Hello, welcome to the lecture on wireless and short-range threats, which is part of this Safety-Informed Security lecture series. The lecture maps mainly to two cyber knowledge areas. The first is the network security because we examine wireless network threats, authentication mechanisms, rogue access point, management traffic, protocol weaknesses, and denial of service attacks. The second is the physical layer and telecommunication security because wireless attacks often exploit the radio medium directly. This includes eavesdropping, interference, jamming, and other forms of disruption or at or near the physical layer. The lecture also partially connects the cyber physical system security, authentication, authorization, and accountability, and applied cryptography. These areas matter because wireless links are often embedded into cyber physical environment, rely on authentication and trust establishment, and depend on cryptographic mechanisms for confidentiality and integrity. So this is what we're going to cover. The lecture is going to be organized into four main parts. First, we look at the wireless security foundation and the reason wireless communication is inherently exposed. We then exposed Wi-Fi threats, including deauthentication, handshake captures, rogue access point, and others. Third, we look at Bluetooth threats. And fourth, we move to low power and proximity protocol threats, including ZigBee, 6LoWPAN, NFC, and wireless disruption attacks, and so on. So let's start with the wireless security foundation. So wireless is vulnerable. Wireless communication extends the attack surface beyond physical network boundaries. In a wired network, an attacker normally needs access to a cable, a switch, port, or some other network connection point. In a wireless network, however, signals are broadcast through the environment. Anyone nearby with suitable equipment may be able to observe, interfere with, or attempt to interact with the communication. And this gives wireless systems several distinctive weaknesses. First, wireless is a broadcast medium. Signals can be received by nearby devices, not only the intended receiver. And this, of course, creates opportunity for eavesdropping, traffic capture, and reconnaissance. Second, the physical layer is exposed as well. Attackers may observe radioactivity, interfere with it, or disrupt it. And this is especially important because radio communication depends on frequency, distance, power, and environmental conditions. And the third is wireless system often share spectrum, which means Wi-Fi, Bluetooth, ZigBee, and other technology may operate in overlapping or nearby frequency bands. And this increases the risk of interference. And fourth, wireless connectivity is dynamic, which means devices move, disconnect, reconnect, roam between access points, and interact with changing network conditions. That mobility creates additional opportunities for spoofing, reconnection attacks, and rogue infrastructure. In a safety-relevant system, these wireless links may carry sensor data, commands, alerts, or monitoring information. If the wireless link is disrupted or manipulated, the safety effect depends on what that link is being used for. So how do we analyze wireless attacks? To analyze wireless attack clearly, we can use four questions. The first question is the target. What part of the wireless system is being attacked? This may be the radio channel, the access point, the client device, the pairing process, the authentication exchange, or the protocol implementation. The second question is the mechanism. How does the attacker exploit the weakness? For example, the attacker may capture traffic, forge management frames, create a rogue access point, replay packets, relay proximity communication, or transmit interference. And the third question is the security impact. Which security property is affected? Some attacks mainly affect confidentiality, for example, eavesdropping. Others affect integrity, such as spoofing sensor data. Others affect availability, such as jamming or deauthentication. And some attacks affect authentication by allowing impersonation or weak trust establishment. And the first question is the safety relevance. What happens if the affected link carries comments, alerts, readings, or status information? And the last question is quite critical. The same wireless attack can have very different safety implications depending on the system context. Disconnecting a personal device from Wi-Fi is not the same as disrupting a medical monitoring gateway or a building automation sensor network. So let's look at specific threats for the different infrastructure environments that we're looking at. So let's look how wireless Wi-Fi security evolved. Wi-Fi security has evolved over time to improve authentication, encryption, and resistance to common wireless attacks. WEP was an early protection mechanism based on RC4. It's historically important, but it had weak key management and repeated initialization vectors, and these design weaknesses made practical key recovery possible. WPA was introduced as a transitional improvement before WPA2. It used TKIP to address some WEP weaknesses, but it was still a transitional mechanism rather than a long-term solution. WPA2 introduced stronger AES-based protection using CCMP. It became the dominant Wi-Fi security standard for many years. However, WPA2 network can still be affected by weak passwords, misconfiguration, and protocol level or implementation level issues. Now, WPA3 introduced SAE to improve protection against offline password guessing. WPA3 provides stronger protection for modern wireless networks, although the overall security still depends on configuration, device support, and implementation quality. The important point is that Wi-Fi security has improved over time, but wireless exposure does not disappear. Attacker might still target authentication, management traffic, access point, trust, passwords, protocol handling, and implementation behavior. So what are the common Wi-Fi security threats? Wi-Fi threats expose radio communication, weak authentication, management traffic, and trust in nearby access point. Eavesdropping is the simplest example. Because Wi-Fi is wireless, an attacker nearby may capture traffic transmitted over the air. Encryption reduces what the attacker can learn, but traffic metadata and misconfigured network may still expose useful information. Weak passwords attacks are another common threat. In WPA2 personnel, an attacker may capture authentication material and then test candidate passphrase offline. The strength of the network can therefore depend heavily on how strong is the password itself. Management frame attacks exploit the fact that some Wi-Fi management frames were historically not protected. The authentication, the association frames can be forced to disrupt client connection. Rogue access points are fake or unauthorized access points. Attackers use them to attack users or devices, observe traffic, redirect communication, or capture credentials. And finally, protocol flows are weaknesses in the Wi-Fi protocol itself or in its implementation. These attacks show that even strong encryption can be undermined if protocol state is handled incorrectly. Older Wi-Fi mechanisms remain useful because they show how weak design choices lead to practical attacks. WEP key recovery is a classic example where you have weak IV handling and RC4 usage allowed attackers to collect enough traffic to recover the network key. Replay attacks as well involve capturing frames and reusing them. If a protocol does not provide adequate freshness protection, replayed messages may generate traffic or trigger repeated behavior. Packet injections allowed attackers to insert crafted frames when protocol protections are weak. In wireless networks, this can be especially powerful because the attacker does not need a physical network port. Weak compatibility mechanisms are also at risk because compatibility can support transition from older systems to newer systems, but it may also preserve weak behaviors or encourage insecure configurations. And the important thing to consider here is that legacy mechanisms are not just historical examples, they help explain why modern wireless systems need careful protocol design, strong key management, and secure default configuration. Let's look at the Wi-Fi attack deauthentication. Deauthentication frames are Wi-Fi management frames used to determine client connection. In a deauthentication attack, the attacker forges deauthentication frames and sends them to a client, an access point, or both. The client believes it has been disconnected and then attempts to reconnect. The main effect is usually availability disruption. The client is forced off the network, and if the attack is repeated, the client may remain disconnected or experience unstable connectivity. Deauthentication is also part of other attacks. For example, forcing a client to reconnect may allow an attacker to capture a WPA2 handshake during the reconnection process. And the weakness is that legacy management frames were not always protected against spoofing. This means an attacker could send frames that appear to come from the access point or client. Now, if you put it in the context of safety-relevant systems, repeated deauthentication may disrupt monitoring, delay alert, or force gateways and devices into repeated reconnection cycles. Protected management frames should be used where supported, and repeated deauthentication patterns should be monitored. This is an example of a handshake capture in WPA2 Personal, where the four-way handshake device derives session keys from the shared passphrase and exchange nonces. The diagram shows the client and access point exchanging 4 messages. The access point sends a nonce, the client responds with its own nonce and the message integrity code. The access point confirms key material and the client acknowledges. An attacker does not need to know the passphrase to capture this exchange. However, they only need to be within wireless range at the time of the connection. Once the handshake is captured, the attacker can perform offline guessing of the password. They test candidate passwords against the captured message integrity code. Predictable or reused from a weak pattern. It may be cracked without further interaction with the network. This is why strong passphrase matters in safety relevant systems. WPA2 Personal should use strong passphrase where it's used at all. For higher assurance environment, enterprise authentication is usually more appropriate. Another example is the evil twin access point. An evil twin is a rogue access point that imitates a legitimate Wi-Fi network. The attackers create a fake access point with familiar SSID, and users and devices, sensors, may usually select it, or devices may connect automatically if they recognize the network name and the configuration allows it. Once a user or device connects, the attacker may observe, redirect, or manipulate traffic. The attacker may present captive portals, capture credentials, redirect DNS, or place the victims into a hostile network environment. The security risk is not only that traffic may be exposed, the larger issue is misplaced trust. The user or device believes it's connected to a legitimate network, but in reality they are connected to the attacker infrastructure. And in safety-relevant design, this becomes more important. Devices should not rely only on the visible network name. Secure wireless communication depends on cryptography, protocol design, and correct implementation. And similarly, rogue access point. In a rogue access point, WPA2 Enterprises uses 802.1x and EAP to authenticate users through an authentication server. It does not rely on a single shared Wi-Fi passphrase. This is stronger than WPA2 Personal when configured correctly, but it introduces its own trust assumption. The client must validate that it's talking to the correct authentication server. In a rogue access point attack, the attacker creates an access point using the same enterprise SSID. If client devices do not correctly validate the server certificate, user may attempt to authenticate to the attacker's infrastructure. And this can expose authentication material and may support offline password guessing, depending on the EAP method and configuration. And the key control is proper certificate validation, where in safety-relevant systems, clients should validate server certificate and use stronger EAP methods such as EAP TLS where possible. And finally, we will move to crack attack. Crack stands for key reinitialization attack. This is a WPA2 attack that exploits vulnerable WPA2 clients. So it attacks the clients, specifically sensors in our case, that reinstall an already used key after a retransmitted handshake message. The problem is not that the Wi-Fi password is guessed. The problem is how vulnerable clients handle retransmitted handshake messages and key state. This diagram shows an access point, a client, and an attacker. During the handshake, message 3 is sent from the access point to the client. The attacker then replays message 3. A vulnerable client may reinstall the same key. This can reset nonce counters. Nonce reuse is dangerous because many encryption schemes depend on nonce not being reused with the same key. If this assumption is broken, confidentiality and integrity protection mechanisms may be weakened. And this attack shows that protocol state handling is critical. Even when encryption is strong, incorrect implementation behavior can undermine the security assumptions of the protocol. Now, the security implications of crack itself there's quite a lot of different several important security implications on crack. First, it does not require guessing the Wi-Fi password. You don't need to know the password. Second, it exploits protocol state handling. That attack depends on how a client processes retransmitted handshake messages and whether it reinstalls key incorrectly. And third, it can weaken confidentiality and integrity. The exact impact depends on the client, the implementation, and the network configuration. And fourth, it depends on vulnerable client behavior. This matters because two devices may support the same standard but behave completely differently. Crack also shows that strong encryption is not enough on its own. Handshake message must be handled correctly. Key reuse and nonce reuse can break security assumptions. Protocol implementation matters as much as protocol design. And in safe to relevant systems, this becomes more important. Wireless security depends on cryptography, protocol design, and correct implementation together. Let's now look at the Bluetooth security threats. Bluetooth security evolution. Bluetooth security has evolved across several different versions. Early Bluetooth relied on pin-based pairing and weaker assumptions about authentication. This created risk where users selected weak pins and pairing happened without sufficient verification. Secure simple pairing improved pairing for Bluetooth classic devices. It introduced better pairing models and reduced some earlier weaknesses. Bluetooth Low Energy, or BLE, was designed for low-power devices such as sensors, wearables, medical devices, and IoT systems. BLE changed the communication model and introduced its own security consideration. LE security connection strengthened BLE pairing using elliptic curve key exchange. This improved resistance to some pairing attacks where devices support and correctly use the stronger mode. Modern Bluetooth includes stronger privacy and security features. However, security still depends on version, pairing mode, device configuration, and implementation quality. Bluetooth architecture includes different communication modes with different power, performance, and security characteristics. Bluetooth Classic is used for audio, peripheral, and continuous connection, and is common in headset, keyboards, cards, and other connected devices. Bluetooth Low Energy is used for sensors, wearable, medical devices, beacons, and IoT devices. It's designed for low power consumption and intermittent communication. The security models differ across Classic and BLE. Pairing, encryption, authentication, reconnection, and privacy features are not identical. Dual mode devices support both Classic and BLE, and this increases compatibility, but it also increases complexity. More supported modes can mean more codes paths, more configuration states, and more opportunities for implementation mistakes. Attack feasibility depends on version, device role, pairing mode, and implementation behavior. Bluetooth attacks often exploit gaps, between supported features, configured security, and what the implementation actually does. Now let's look at the common Bluetooth security threats. Bluetooth threats exploit short-range discovery, pairing, authentication, and implementation weaknesses. Device discovery exposes nearby devices and services to potential attackers. For example, a device that advertises itself may reveal its type, role, or available services. Weak pairing is also a major risk. If devices establish trust with limited verifications, attackers may be able to impersonate a peer device or position themselves between devices. Eavesdropping may be possible where encryption is absent, weak, or undermined by pairing weaknesses. Man-in-the-middle attacks occur when an attacker positions themselves between paired devices, relays messages, and potentially observes or modifies communication. Implementation flows in Bluetooth can expose devices remotely or from short range. These vulnerabilities are particularly concerning because Bluetooth is often enabled by default. And tracking is another important issue, especially in BLE. Advertising can reveal device presence, movement, or behavior if identifiers or patterns are stable enough to observe over time. Bluetooth pairing establishes shared keys so devices can authenticate and encrypt later communication. The goal of pairing is to establish trust between two nearby Bluetooth devices. Once paired, the devices can use stored key material for later communication. During key establishment, devices negotiate or derive keys. The strength of this process depends on the pairing method and on the amount of user interaction involved. Pairing methods with strong user verification provide better protection against impersonation and man-in-the-middle attacks. Pairing methods with limited or absent verification are often weaker. And weak pairing can undermine later encryption. If the attacker interferes during pairing or tricks devices into trusting the wrong peer, later encrypted communication may still be exposed or controlled. Pairing is therefore a critical point where Bluetooth security can be weakened before normal communication begins. Weak Bluetooth pairing occurs when devices establish trust without strong authentication of the peer device, and that leads to man-in-the-middle attack. For example, a common example is pairing with limited user verification such as just works. This may be acceptable for some low-risk context, but it's weaker against man-in-the-middle attacks. In a man-in-the-middle attack scenario, the attacker replays pairing messages between two nearby devices. Each device may believe it's pairing directly with the other device, while the attacker is actually positioned between them. The authentication gap is that the devices may establish keys without confirming the peer strongly enough. And if this happens, encrypted communication may be exposed or controlled by the attacker. This is particularly important in safety-relevant use, where paired devices may exchange readings, comments, alerts, or status data. A weak pairing process can therefore affect the trustworthiness of the operational information. Now let's look at BLE advertising, discovering, and tracking, and how BLE devices use advertising packets to announce their presence before or between connection. Advertising allows nearby scanners to observe devices without pairing. This is useful for discovery and low-power communication, but it also creates privacy and security exposures. Advertising packets may contain identifiers, service UUIDs, names, or connection information. If these values reveal the device type or role, the attacker may learn what kind of device is nearby. Stable identifiers or recognizable advertising patterns can support tracking. Repeated observation movement may reveal movement, presence, or behavior pattern. There's also the data exposure risk, where poor implementation may expose sensitive values before even encryption happens, or include too much operational information in advertising packets. And in safety-relevant system, advertising data may expose device presence, roles, or operational context. Even if the attacker cannot connect, passive observation may still reveal useful information. Let's look at some vulnerabilities for Bluetooth protocol itself. Blueborn is one vulnerability that refers to Bluetooth stack vulnerabilities that can allow nearby attacks to target affected devices without pairing. The attack surface is a Bluetooth stack on nearby Bluetooth-enabled device. The attacker must be within Bluetooth radio range, but the victim device may not need to be paired with the attacker. And the main weakness here is the implementation flow in the Bluetooth protocol handling. These are not simply weak passwords or bad user choices, they are vulnerabilities in the software stack that processes the Bluetooth communication. And the security impact may include device compromise, data exposure, or network pivoting. A compromised Bluetooth-enabled device could become a path into a wider network. And safety-relevant system-affected Bluetooth links may carry comments, readings, alerts, or device status. And a stack-level vulnerability can therefore affect both the local device and any system that trusts its data. Another Bluetooth vulnerability is nub and bias. Nub and bias show how Bluetooth security can be weakened by flaws in the key negotiation and authentication assumptions. Nub forces weaker encryption key negotiation in vulnerable Bluetooth classic connections. The result is a reduction in effective encryption threats. Bias allows impersonation of a paired device under vulnerable authentication handling. The attack challenges assumptions about trust in previously paired devices, and the attack surface includes Bluetooth classic pairing, key negotiation, and also reconnection. These are not purely application level again. They affect the trust and the cryptographic assumption of the Bluetooth connection itself. And the security impact may include weakened confidentiality, authentication, or even device trust. And in safety-relevant systems, protocol level weaknesses may persist, even when devices appear paired and encrypted. And a system may look secure at the user interface level while its underlying assumptions have been weakened. We now move to low power and proximity controls. Low power and proximity control support constrained devices, short-range interaction, and IoT communication. Zigbee is an example of low-power networks that uses low-power mesh networking, including sensors, automations, and IoT devices. Z-Wave is common in smart home mesh networking. It uses controllers, devices, and inclusion processes to add devices to the network. Thread is an IPv6-based low-power mesh networking protocol for IoT communication. NFC and RFID support proximity communication for tagged access points or access systems, contactless exchange, and identity-related interactions. LoRaWAN supports long-range, low-power communication for telemetry and remote sensing. And these protocols are often used in constrained environments. Devices may have limited processing power, limited memory, limited battery capacity, and long deployment lifetime. And in safety-relevant systems, constrained links may carry sensor readings, comments, alarms, or status. The low-power nature does not make them low risk. Common low-power and proximity threats include protocols that expose threats around joining, identity, relay, replay, and radio disruption. Weak joining occurs when devices enter a network through insecure or poorly protected processes. If joining is weak, an attacker may add unauthorized devices or capture sensitive key materials. Key exposure is a serious concern. Shared, default, or poorly protected keys can expose multiple devices at once. Replay attacks involve capturing messages and reusing them later. Without freshness checks, the receiver may accept all messages as if they are current. Relay attacks bypass proximity assumptions by forwarding messages between endpoints. This is especially relevant for NFC and access systems. Device spoofing, on the other hand, occurs when attackers imitate sensors, tags, or controllers. If the system trusts identity too easily, spoofed devices may influence decisions. Radio disruptions affect availability. Low power links may be especially vulnerable to interference because devices have limited transmission power and limited energy reserves. And in safety-relevant systems, these links may carry measurement again, commands, alarms, or state changes. Sixth low-PAN surface is a threat. Sixth low-PAN brings IP networking into constrained wireless networks. This creates threats around identity, fragmentation, routing, and gateway trust. Fragmentation abuse is a concern because constrained devices have limited power, malformed, or excessive fragments may disrupt reassembly or exhaust messages and resources. Node spoofing occurs when attackers imitate constrained devices, and if identity checks are weak, false data or false control traffic may enter the network. Replay again is possible where packets are captured and reused without freshness protection. And router disruption can occur when compromised nodes influence forwarding. In mesh or constrained network, one bad node can affect communication paths for others. And finally, the border router is especially important because it connects constrained wireless network to wider IP networks. That make it a key trust boundary. In safety-relevant systems, affected 6LoWPAN links may delay, alter, or block measurements, commands, alerts, or state updates. ZigBee attacks are another example. One particular example is joining and key exposure. ZigBee devices may receive network keys during joining. This makes joining a critical security point. The attack target is devices joining, rejoining, or commissioning. If an attacker can observe or influence this process, they may gain access to key material. And key exposure allows the attacker to decrypt traffic, inject traffic, or impersonate devices depending on the system configuration. Default keys are particularly risky. If many devices rely on the same known or predictable key, one weakness can affect many deployments. Device spoofing is another consequence. Attacker may imitate sensors, switches, or controllers if they gain sufficient knowledge of the network. In safety-relevant systems, exposed ZigBee links may affect sensors, sensor reading, commands, alarms, or device state. And finally, NFC attack. An example of NFC attacks, the relay attack. NFC relay attacks forward communication between a legitimate reader and token, bypassing the expected proximity assumption. NFC systems often assume that if a token can communicate with the reader, the token must be physically nearby. Relay attacks challenge that assumption. The attacker forwards messages between distant legitimate endpoints. The reader believes the token is nearby, and the token believes it's interacting with the legitimate reader. The security impact may include unauthorized access or unauthorized transactions. Feasibility depends on timing, distance, and protocol checks. Some systems include protections that make relay attack harder, but proximity alone should not be treated as a complete security guarantee. In safety-relevant systems, proximity assumption may protect access, commands, identity, or authorization. If this proximity assumption is bypassed, the system may grant trust in the wrong context. And finally, we will move to wireless disruption attacks. In a wireless disruption attacks interfere with radio communication and reduce the ability of devices to exchange data reliably. Jamming, for example, is the direct use of radio interference to prevent successful transmission or reception. Interference, on the other hand, may also come from other devices operating on shared spectrum. Not all interference is malicious. However, attackers can intentionally create or exploit it. Congestion occurs when excess traffic reduces availability and increases delay. Wireless capacity is limited and crowded channels can degrade performance quickly. Depletion attacks target constrained devices by forcing them to spend energy on repeated communication processing, retries, or connection attempts. Denial of service occurs when devices lose connectivity, delay messages, or miss state updates. In safety-relevant systems, disrupted wireless link may delay or block comments, alerts, measurement, or status updates. Wireless attack jamming, for example. Jamming disrupts radio communication by transmitting interference on the same or nearby frequencies. The attack target is wireless availability at the physical or link layer. The attacker is not necessarily trying to read or modify the message. They may simply prevent communication from working reliably. The attack method is interference. If receiver cannot decode legitimate signals, communication fails or becomes unreliable. And many systems can be affected by this, including Wi-Fi, Bluetooth, Zigbee, LoRaWAN, and other radio systems. The details vary, but the basic availability problem is shared. The denial of service impact include disconnection, delayed message, missed report, and loss of state visibility. And the scope depends on power, frequency, distance, and environment. A high-power jammer can affect a wider area, but even local interference may be enough to disrupt a concerned system. And in safety system, jamming may block alerts, comments, measurements, or status updates. And finally, wireless denial of service, or congestion and depletion. Wireless denial of service attacks can reduce availability by exhausting channel capacity, device energy, or protocol state. Traffic flooding consumes bandwidth and processing capacity. Even if messages are not valid, receiving and discarding them can still cost resources, for example, in low-power devices with battery-power operated devices. Connection abuse involves repeated connection attempts, association requests, or pairing attempts. Devices may waste resources handling these repeated interactions, and battery depletion is especially important for constrained devices. A device that should operate for months or years may be forced to spend energy on unnecessary traffic. Protocol abuse exploits retries, acknowledgement, association processes, or other protocol behavior. The attackers take advantage of the work the protocol requires the victim to perform. The availability impact is the devices may become slow, unreachable, or unstable. And in safety-relevant system, wireless denial of service may delay comments, alerts, measurements, or status updates. In this lecture, we have examined wireless and short-range threats across several different technologies. Wireless exposure is the starting point. Broadcast communication extends the attack surface beyond physical boundaries. We talk about Wi-Fi threats that might exploit authentication, management frames, rogue access point, protocol behavior, and implementation weaknesses. We looked at Bluetooth threats, including pairing weaknesses, discovery, exposure, tracking, man-in-the-middle attack, and stack vulnerability. We also explored low-power protocols that introduce risks around joining, key exposure, relay, replay, and spoofing and constrained device limitations. We finally looked at disruption attacks and availability attacks such as jamming and wireless denial of service, which reduce availability across wireless systems. The key point for security-informed system is that wireless threats may affect commands, alerts, measurement, or device state. Once wireless communication supports operational or physical processes, security failures can become safety relevant. When analyzing wireless systems, we should not stop at asking whether an attack is technically possible. We also need to ask what the affected communication is used for. If the wireless link carries routine web traffic, the impact may be limited to confidentiality or availability of information. However, if it carries patient reading access, control decisions, building automation commands, or industrial sensor data, the same technical attack may have a direct operational or safety implication. This is the bridge between wireless security and the security-informed safety. And these are key references that you can look at for topics that we discussed in today's lecture. Thank you.